Welcome, my name is Schoene and I talk about the improvements that we made for our processor stress test FIRESTARTER and how we integrated dynamic code generation into our tool. What are processor stress tests and why are they needed? Well, what you see here on that slide, that's the power consumption of a single compute node of our system Taurus. It hosts two Haswell processors and 4 NVIDIA K80 graphics cards. And you see that the power consumption of the node varies between 200 watt and 800 watt. So here, that purple region, here, that's over 1 week, the power consumption. The purple region, that spans the minimum and the maximum, and here that dotted line, that's the average power consumption. And if you just purchase a system and you want to check whether the cooling suffers and whether the power infrastructure, the power supply infrastructure works for the hardware that you're about to purchase, you just need some stress test which increases the power consumption so that you can be sure that there's no user-generated workload that would run out of the specifications that you tested. And for that, we need some stress tests that increase the power consumption. What belongs to the power consumption? So what are the parts that influence the power consumption of process of integrated circuits? So that's a formula you probably already know. The first part here is the dynamic power consumption, which consists of that alpha and that capacity, so the activation factor and capacity of the processor. And this is influenced by the workload that is executed, so how many cores are you using, which executions units are you using, so SIMD or arithmetic logical units or both at the same time, what data are you using in the computation. So that is plays into that factor. Then you have that V squared and F, so voltage squared and times frequency. That depends on the frequency that is applied, which then defines the voltage that is applied to the cores or the other components that are on the processors, and that's influenced by that. Then the second part, that current times voltage, that's the static power consumption, which is then also influenced by idle states, which will decrease that I and the whole factor of that, and by the voltage, which is influenced by the dynamic voltage and frequency scaling, for example. What you see here on the right side is how they contribute. So we start with an idling node without GPUs and with GPUs, and then you say, okay, I don't want the CPU cores to idle, the processor cores, but run something within the register at low demanding workload, a high demanding workload, adding memory references for the different cache and memory levels, and then in the end you also add the GPUs for computation. That means in the idle case you have a 200 watts, and that's what we've seen before, and if you have a high demanding workload, it goes up to 1.1 kilowatt. And that is what just goes in there in the computation. To test that and to create such a high demanding workload, a stress test, there's different software available, for example Prime or M Prime, which performs Lucas Lehman test and runs AVX and AVX 512 instructions, also adds memory references, and all of that increases the power consumption of the system. There's LinPack, where you have a preparation phase and then a computation phase with the linear equation, and then it's validated. And also here you have the AVX 512 instructions and some, not as many memory references. That's why you see there's a difference here in the power consumption, which we showed in a previous paper. There are other stress tests which are not targeted at generating high power consumption, but are used to stress, for example, the operating system or the I/O system. And then there's our work FIRESTARTER, which is the red line here. So what is the principle of FIRESTARTER? The principle of FIRESTARTER is that it has three factors that we are changing. The first is a set of instructions. So whether you use SSE instructions or AVX or AVX 512 instructions, whether you use FMA or not. So that's the set of instructions, and we typically want to choose the set of instructions in a way that it's not limited by any factor. So we want to stress all parts of the processor, the front end, which decodes the instructions, the back end, which executes the instructions, and the memory hierarchy, which is used to load and store operands. So we have the set of instructions, and the set of instructions that are executed will stress this back end, so the SIMD units, the arithmetic logical units, and so on. Then we have the unroll factor, and the unroll factor will unroll the instructions that we have in a way that they won't fit into that micro-op buffer anymore. So usually you have a micro-op buffer where you put in your decoded instructions, and if that inner loop that you have fits into that micro-op buffer, they don't have to be fetched from L1 instruction cache and don't have to be decoded. So we have the unroll factor, and with that we will make sure that that internal loop is big enough that it doesn't fit in the micro buffer, but only in the level 1 instruction cache. And then we have memory references, which are used then for the instructions that will load data from the different memory levels. And as you can see down there, they can have loads, they can have stores, or they can have both. In FIRESTARTER 1, the design was the following. We had some templates which defined the instruction set, the unroll factor, and the memory references that were used from these templates, which existed per processor model. You created files, C files, which are then compiled into the binary, and then we had a binary with a lot of these workloads that could be executed, and during runtime the binary would check the processor model and use the best fitting workload that was there. So within that binary you have a lot of those unrolled workloads with memory references and certain instructions. In FIRESTARTER 2 we changed that design, and now only the sets of instructions are within the code, and everything else will be applied at runtime. So you have in the code the set of instructions, AVX 512, AVX plus FMA, SSE, everything that's in the source code, and then you compile everything and ASMJIT into the binary. ASMJIT is our just-in-time compiler, which we'll use at runtime. So at runtime we also check the processor model, as we did in FIRESTARTER 1, and then we choose the instructions that we want to use to stress the backend. Then we'll check the size of the level 1 instruction cache and unroll it. Then we'll check the memory references that we think are best for that workload, and then we'll create such a workload which is then compiled at runtime to be executed afterwards. So all of that is during the initialization phase of FIRESTARTER. And yeah, also we have here the GPU code still there. So we switched everything from compilation to runtime to make it easier to adapt FIRESTARTER to your specific system. Because, well, there's no single optimal workload for a specific processor model. It highly depends on the SKU. For example, if you have a varying frequency, so multiple processor models with different frequencies, then, and all the rest is the same, then the one with a higher frequency should have less memory references per cycle than the one with lower frequency, if we assume that the memory bandwidths and latencies are independent of the processor frequency. And therefore, in that case, for the processor with a higher frequency, we would introduce less memory references, just to make sure that the workload won't stall. Okay, so we go away from that thinking that there's a single best workload for a specific processor model, and that's where the automated tuning comes in. We integrated some metrics. There are some internal metrics like instructions measurement and cycle measurement via the perf interface. There's a RAPL measurement via sysfs and also perf, I guess. And you can also integrate external metrics. For example, if you have a script, then you can apply that, and whatever that script's write to standard out can be used as another metric within FIRESTARTER 2, or you can write a library which provides you a metric. So you can also add some external metrics to do the automated tuning. And this automated tuning will use an NSGA2 algorithm, a genetic algorithm, and will just create several generations of configurations. So what is the best number of memory references to each of the levels, and it will come up in the end with a good solution for your system. On the other changes, so we made sure that the data is initialized in a way that there are no special cases which could lead to a reduced power consumption. So there should never be 1 or 0 or an infinite within the register. We integrated, since we already have the metrics, performance measurement, so that you can say, I want to have a comma-separated value output after the runtime of FIRESTARTER, which tells me what is the instructions per cycle, what is the average power consumption, and so on. You can flush the register content, which is good if you are using an overclocking scenario, and then the sim units, for example, could provide an incorrect output because they are out of the specification, and then bits could flip, for example. And if you want to avoid that, and if you want to check that, then you can use that option to flush the register content in a specific interval to check whether the solution that you have is still correct. Then there's more CUDA support, Zen2 support, and macOS support. Speaking of Zen2, that is a test system that we use in the following slides, where we just look on how FIRESTARTER 2 will behave and how the factors will contribute to the power consumption. The factors U and M, annual factor and memory references. As instructions, we use 2 FMA instructions with 256-bit width, so AVX, 256-bit FMA instructions, and 2 ALU instructions with a shift, left, right, all the time, and an XOR just to toggle the bits in the ALU and increasing power consumption even more. So first let's look at the unroll factor. What we do here is that we don't have memory references, we only have references to registers, and then we change the loop size. So we change the size of instructions within the inner loop that will execute the workload, and that will then increase the power consumption. We have 4 phases. In the first phase, there's a specific overhead for the loop, so you have the jump back to the beginning of the loop, and you have some comparisons that whether you want to leave the loop, and that contributes to unusual high instruction throughput. So what you see here is for increasing annual factor, the power consumption for 1.5, 2.2 and 2.5 gigahertz, and here you have the instruction throughput for all of these frequencies, and they are overlapping, so it's not really visible. In the beginning, the overhead of the loop header is really high, so you have higher than 4.0 instructions per cycle throughput, which is not surprising. But 4.0, that's what we would target, because that's what we have when we look at the 4 instructions that we want to perform. 2 FMA, shift, XOR. Then we run in the micro op buffer or in the op buffer, and everything is fine. And here the power consumption increases then when the loop is too big to be in the micro buffer, but has to be loaded and decoded from the level 1 instruction cache. If you then go to the level 2 instruction cache, the power consumption increases even more, but not here for that case where we go to where we have 2.5 gigahertz. Here it decreases because the set frequency of 2.5 gigahertz will be lowered because the processor assumes that it runs too hot, that it has a power consumption that is too high for the TDP, and therefore it will lower the frequency below the nominal frequency. Now that we know that the highest power consumption that we have, if we do not want to stress other levels, is with the level 1 cache, and we want to have the level 2 cache more for the memory references that provide operands for the computation. So we have the high power consumption from the level 1 instruction cache, loading instructions from there and decoding them, and now we add memory references to the workload. Here we start again in the registers. We go the green bar, that's the one for the power consumption. We start the registers, level 1, level 2, level 3, and added main memory. So we always add another level of memory that is accessed. And then we come here to that power consumption at 1.5 gigahertz. So we used 1.5 gigahertz here to avoid that effect that the processor clocks down, and then we would just have another level of abstraction here. We just use the 1.5 to make sure that this doesn't happen. Okay, and we have that increasing power consumption here. The instruction throughput in orange is not 4.0 anymore. It's a little less. It goes more into the direction of 3.5 instructions per cycle, but well, it's high enough that you get a high power consumption. So each level of memory contributes to the high power consumption. What we did there in the last step is that we added references to the next memory level and then checked and tuned what was the best performing one so the best performing factor for that memory level, and then we stuck there and so on and so on. And here you see what happens if you leave everything out and say, I want to just find the optimal power consumption when I tune for all memory accesses, so for L1, 2, 3 and main memory. Here you have the power on the x-axis and the instruction throughput on the y-axis, and it varies the memory references and learns here from each generation. You see that the older the generation is, so the first generations are here pretty light and you won't see them that detailed, and they get darker the older the generation is, and here that is the optimum here, the orange dot with the highest power consumption. So here we just can show that the tuning for power consumption just works. And the self-tuning doesn't only work for the 1.5 gigahertz, but also for other frequencies. And that is the reason why we introduced that we have different workloads for different SKUs and for different number of cores and different number of different frequencies that we have. So here we compare the workloads that have the highest power consumption when tuned at y-axis 1.5, 2.2 and 2.5 gigahertz. On the left side you see the power consumption, on the middle you see the instructions per cycle, and here on the right side you see the applied frequency during runtime. So what you see on the left side is that each workload that was tuned for a specific frequency runs best for that frequency. So the workload that was optimized for 1.5 gigahertz has the highest power consumption at 1.5 gigahertz and not any other workload that was optimized for that. And that is also true for 2.2 gigahertz optimized, run at 2.2 gigahertz. So that's the diagonal from the lower left to the top right on the left heat map. What you see here in the middle is that you have if you go from right to left, you have an increasing instructions per cycle. So when you tune for 2.5 gigahertz and run at 2.5 gigahertz, you will have 2.39 instructions per cycle. But if you lower the frequency, then you will not have as many stalls due to memory accesses, and with that the instructions per cycle will increase. So 2.39 to 2.5 to 3.42 instructions per cycle. Except here for that lower case, where you tuned for 1.5 gigahertz and then it runs with more instructions per cycle at 2.5 compared to 2.2 gigahertz. But we can explain that with the applied frequency. We set the frequency to 2.2 and 2.5 gigahertz, but the applied frequency after it is throttled, because the processor assumes that it uses more than its TDP, will just go down. And it goes more down here at 2.5 gigahertz, and with that the cycle is worth more here. And that is the effect that we see here, the 2%. So the 1% here is also reflected here. So that is then the thing that we see here, the effect of the frequency change. To sum it up, we have a new version of FIRESTARTER, try it out. It includes internal and external metrics, which you can also report when you run FIRESTARTER. We can create now the workload at runtime and not during compile time only. You have an automatic tuning algorithm which uses the metrics that are integrated and that you can apply from external to find an optimal solution for your processing node. And we've shown that there is no single optimal workload for a processor model. It's highly SKU specific, and it's probably not only SKU specific, but also specific for a specific processor. And you can, with FIRESTARTER 2, provide the perfect benchmark stress test for that processor that you have. FIRESTARTER is available on GitHub. All the data that are presented here and in the paper is available on GitHub. So just fork it and do with it whatever you want. Probably run FIRESTARTER. And if there are any questions, I will answer them in the chat. But before I say thank you for listening, thank you to the co-authors of that paper, and I'll be in the chat answering your questions right now.